Welcome back, chemists. We've been talking about matter and how we separate it, and now we're going to work on how to identify different substances. So remember in the last video we talked about different techniques like distillation and chromatography, methods that you can use to separate a mixture, whether it's a food mixture or anything, into pure substances. Well, once you have those pure substances, how do you identify what that substance is? When you're making something in the laboratory, quite often it just looks like a white solid or a colorless liquid, and many substances have those properties, so how can you tell what something is? Today we're going to look at chemical tests, some physical tests, and then talk about forces of attraction that explain some of the things that we can see to attempt to start to identify the properties of a substance. I'm going to kick it off with a video from our very own classroom that shows what's called the Tollens silver mirror test. So this is the synthesis of a silver reagent, known as the Tollens reagent. It first involves making silver in solution in the presence of base, and we do that by making what's called a complex ion, a silver ammonia complex ion. So that first part is just making the Tollens reagent. And then when you react the Tollens reagent with any substance that contains what's called an aldehyde, you get a positive result. In this case, you get a silver mirror, and there it is, coating the inside of the flask. Very reflective, shiny silver mirror on the inside of that flask. To get the flask back, you can oxidize the silver with nitric acid, and then that actually turns it back into aqueous silver ion. So that's a very old-fashioned test, but still used a lot in the laboratory to detect whether or not you have what's called an aldehyde. So if you look at your notes, the first one is the Tollens test, and this is exploiting silver ion, Ag+, reacts with an aldehyde group. That's a type of what's called functional group in an organic molecule, and if it's there, you'll form silver. So this is a binary test. You either have an aldehyde or you don't. The demonstration video that you just saw was a test for glucose, which is an aldehyde containing sugar. In fact, there it is in the upper right of your notes right there, showing how it oxidizes the glucose, and more importantly for the test, it reduces the silver ion down to silver metal, and you get that coated glassware. Another chemical test, maybe you've seen this, it's more related to foods, is the starch-iodine test. Starch notoriously reacts with iodine to give a very dark blue-black complex. There's a short video of it courtesy of the Periodic Videos group out of the University of Nottingham, showing an iodine clock reaction which takes advantage of this property of starch and iodine. And there's the very dark color that you see at the end there. And then a very common chemical test relies on what are called pH indicator molecules. These are organic molecules like the bromthymol blue one over there. And they change color depending on how acidic or basic your mixture is. And there's an animated GIF that shows what's called universal indicator, which is usually a mixture of at least 3 different indicator molecules, and it goes through a series of color changes depending on the pH. Depending on how acidic a solution is, you get different colors in the visible spectrum. And these are just 3, quite common, but only 3 different chemical tests that chemists use to this day. And hopefully it makes sense that you could never use just one of those to actually identify what a chemical substance is. But combining them gives us more information, and we start to learn more about what the structure of a molecule looks like. So combining chemical tests with other tests, let's talk about physical tests. One property to look at is solubility. Substances are usually either water-soluble, such as salts and sugars, or very water-insoluble, let's say organic-soluble. Things like oils and other organic things usually don't go into aqueous media. And you can imagine just checking if something is soluble or not. These, what I'll call physical tests, have the advantage of the fact that they don't chemically change the identity of your substance. The ones we just looked at, the Tollens test, the starch test, and the pH test, those actually require you to chemically change the identity of your substance, which means you have to sacrifice some amount of it in order to tell what the result is. If I check for the solubility of something, I could imagine recovering that substance just by evaporating the solvent. And then in the right there you see what's called a separatory funnel. That's actually a separation technique. If you have 2 liquids that are not mixable, aka they are immiscible, they'll layer on top of each other, like oil and water lay on top of each other, and you can separate them just based on density differences. In addition to solubility, we can look at what temperature is required to change the phase, aka the melting point of a substance. Well, compounds with stronger attractive forces tend to have higher melting points. So if it takes a relatively high temperature to melt some solid into its liquid, we might know something about the types of forces of attraction present in that substance. More commonly, that would be used to actually compare a literature melting point of a known substance with some experimental value that you find yourself. This works for boiling point as well. If a substance has very strong forces of attraction, it will typically have higher boiling temperatures. It takes more energy to separate those molecules apart from each other. That's a physical change, but it still requires just more energy to overcome those interactions. Speaking of interactions, let's relate this to our everyday lives a little bit and close out with what those different forces of attraction look like. On your notes, I just have a handful, or 2 handfuls, I suppose, of some everyday substances that you might find around you. Glass, steel, salt, sugar, copper, aluminum, wax, graphite. Maybe that last one, potassium chlorate, isn't so common, but we certainly have it in our laboratories. Of those substances, if you were to research which ones have the highest melting points and which ones have the lowest boiling points, maybe you're even mentally guessing right now, which you should, you would find roughly those temperatures for the melting points of those solids. And there's quite a range, anything from only around 60 degrees for that chunk of wax, up into the 3000s for that little picture of a sculpture made out of graphite, which is just pure carbon. What explains these drastic differences? Well, it's the 4 categories you see down below. We can break up we can categorize every single substance into one of these 4 categories of matter. They're either a network covalent substance, which both glass and graphite from the row above happen to fall into. A network covalent substance is a network of covalent bonds. There's only a handful that you should know for the purposes of this class. Graphite is one of them. Glass is another. Really, quartz is the crystalline form of silica, or silicon dioxide. And diamond, the allotrope of carbon, the more stable allotrope of carbon, compared to the more common one of graphite. Those are the 3 most common network covalent solids that you'll see in this course. Now, why do they have such high melting points compared to all the others? Well, this is the only category where you actually do break a chemical bond in order to change the phase. You're actually breaking that series of covalent bonds that you see in the model. I think I'm actually right in front of it if I think about where this video is going to end up. And that takes a very high temperature to break covalent bonds. It's almost a chemical change when you think about what that means. Then we get to the next batch, the metals. That would be aluminum, copper, and steel. Steel is actually an alloy of iron and carbon and possibly some other things. An alloy is a solid mixture that behaves like a metal. Steel happens to be an interstitial alloy of large iron atoms and small carbon atoms in the spaces in between. There are other alloys called substitutional alloys like brass and bronze, where atoms are just replaced with atoms of similar size. But nonetheless, it behaves like a metal, and it has a relatively high melting point temperature in the hundreds and maybe low thousands. This depends on what the metal is, but I'll put that as the second one. Why is that? Well, it takes a high energy, it takes a high temperature, a lot of energy to break apart the structure of a metal, which looks like what you see immediately to my right, which are positive nuclei sort of swimming in this sea of delocalized electrons. That's just what the metallic structure looks like for a substance. This also explains why metals conduct electricity and heat very well as why they are malleable, meaning you can bend them and shape them as opposed to being quite brittle. What's brittle are ionic compounds, such as the salt and the potassium chlorate. Those are a lattice in the solid state of cations and anions, and they're brittle because if you try to shear a solid chunk of salt or any ionic compound, it just takes one layer of those ions to displace, and instead of the attraction between positive and negative charges, you get a repulsion with positive right next to each other, and like forces repel one another as opposed to opposite forces attracting each other. Metallic solids and ionic solids both have relatively high melting temperatures, and I don't really have that ranking meant to be an authoritative statement. Sometimes there are certainly ionic compounds that are higher melting than metallic compounds. Case in point, right above, salt melts at around 800, aluminum only 660, give or take. So there's certainly some gray area in which ones have stronger forces of attraction. What's almost always at the bottom of the list are molecular compounds. And molecular compounds are made of discrete molecules. There's a picture of what look like phosphorus molecules, P4 molecules. There's a little tetrahedra in the lower right there. Sugar is also molecular, as is wax. and these just have lower melting temperatures typically than the other substances that we talked about today. We're going to talk a lot more about molecular substances going forward in the class and the different types of forces of attraction that we find specifically in that category, but that's for a later unit in this class. Okay, so this video was meant to introduce you to some of the techniques that chemists use to separate and then more importantly identify different substances. We can test them with different chemical tests. We can investigate their physical properties, solubility, melting temperature. And we can use that information usually in combination with each other to start to figure out what kinds of properties a substance have. Is it acidic? Is it water soluble? Is it relatively low melting? Okay, we could just use those 3 tests we just talked about today to answer that. Moving forward, we're going to look at analytical tests, some really modern techniques that we can actually use to combine with these and decipher what the structure of a substance is.